Look up at the night sky. What do you see? A vast, silent expanse filled with distant stars and galaxies, each one holding secrets we're only beginning to uncover. But hidden within that cosmic silence, there's something far more intriguing, a series of whispers from the depths of space, signals so strange and unexpected that they've left even the most brilliant astronomers scratching their heads. These aren't just random bursts of energy, they're deliberate, powerful, and utterly mysterious. Some arrive in perfect patterns, others vanish as quickly as they appear, and a few even seem to repeat, but none of them have a clear explanation. What could possibly be sending these signals across the universe, and why do they defy everything we think we know about how space behaves? For decades, scientists have been picking up these unexplained galactic signals, each one a puzzle waiting to be solved. Some theories suggest natural phenomena colliding stars, spinning remnants of dead suns, or even the echoes of ancient cosmic explosions. But others, well, they're far more speculative. Could these signals be attempts at communication from civilizations we've yet to discover? Or are we witnessing something entirely new, a force of nature we haven't even begun to understand? The truth is, every time we detect one of these signals, it challenges our assumptions about the universe and our place within it. They're not just scientific curiosities, they're reminders of how much we still have to learn. Today, we're diving deep into 30 of the most baffling signals ever detected, each one stranger than the last. We'll explore the leading theories, from the plausible to the downright mind-bending, and unravel why these cosmic enigmas have captivated researchers for generations. Whether it's a burst of energy that shouldn't exist or a repeating pattern that defies logic, these signals hold clues to some of the universe's biggest mysteries. So if you've ever stared at the stars and wondered what's really out there, you're about to get closer to the answers than ever before. The universe is speaking, we just have to learn how to listen. Of all the unexplained signals ever detected from space, none have captured the imagination quite like the WOW signal. It appeared on August 15, 1977, when a radio telescope in Ohio picked up an intense burst of radiation unlike anything astronomers had ever seen. Lasting a mere 72 seconds, it blasted through a narrow frequency band used by hydrogen, the most common element in the universe, before vanishing without a trace. What made it so remarkable wasn't just its strength, nearly 30 times louder than the background noise of space, but its eerie precision. The signal seemed deliberate, almost engineered, as if something or someone had aimed it directly at Earth. Scientists at the time circled the letters WOW on the printout in disbelief, giving the signal its iconic name. Decades later, we still don't know what caused it. Some argue it could have been a natural event, maybe a comet's hydrogen cloud passing through the telescope's field of view, or an exotic stellar phenomenon like a collapsing neutron star. But here's the problem: no known cosmic object behaves this way. Comets don't emit such focused radio bursts, and neutron stars typically produce repeating pulses, not one-off blips. Then there's the more tantalizing possibility. Could this have been a deliberate transmission? The frequency it used, 1420 MHz, is a quiet spot in the radio spectrum, a natural waterhole where interstellar messages might logically be sent. If it was artificial, the implications are staggering. A civilization advanced enough to project a signal that powerful would have to be far beyond our own technological reach. Yet despite countless searches, the WOW signal never repeated. Was it a fleeting hello from across the cosmos, a malfunction we misinterpreted, or something entirely beyond our current understanding? What keeps this mystery alive isn't just the lack of answers, it's the way this signal defies easy explanation. Every time we think we've ruled out one theory, another hole opens up. Even today, the WOW signal stands as a humbling reminder that the universe still holds puzzles we can't yet solve, and maybe that's the most exciting part of all. Just when we thought fast radio bursts couldn't get any stranger, along came FRB 121102, the first repeating signal of its kind. Discovered in 2012, this cosmic anomaly shattered expectations by doing something no other fast radio burst had done before. It came back. Unlike one-off bursts that flash and disappear forever, this one returned again and again, sending pulses of energy across 3 billion light-years to reach Earth. Each burst lasted mere milliseconds, but packed more energy than the Sun emits in an entire day, leaving astronomers stunned. What could possibly produce such violent, repeating explosions in the depths of space? The leading suspect, magnetars, super-dense, highly magnetic remnants of dead stars. Imagine a neutron star, but with a magnetic field so intense it could strip the data from every credit card on Earth from halfway across the galaxy. When these cosmic powerhouses experience starquakes or magnetic eruptions, they might unleash the staggering energy we detect as fast radio bursts. FRB 121102's repeating pattern fits this idea, like a cosmic distress beacon flickering on and off as the magnetar's crust fractures under unimaginable strain. But there's a twist. This signal originates from a tiny, turbulent dwarf galaxy, a place where star formation runs wild. That environment is packed with the raw materials needed to create magnetars, adding weight to the theory. Yet some bursts from this source show bizarre, intricate structures, sub-pulses within pulses that resemble coded patterns. That level of complexity has led to more radical suggestions. Could we be seeing the exhaust trail of an alien propulsion system, or perhaps a directed energy signal intentionally beamed through the cosmos? The truth is, even after years of study, FRB 121102 refuses to fit neatly into any box. It challenges our understanding of physics, forcing scientists to reconsider how energy behaves under extreme conditions. Every new burst it sends raises fresh questions, turning this distant speck of the universe into one of astronomy's greatest classrooms. Whether it's a natural cosmic powerhouse or something even more extraordinary, one thing's certain: the universe still has plenty of surprises up its sleeve. Some signals tease us with their strangeness just close enough to known physics to seem plausible, yet just bizarre enough to spark endless debate. That's exactly what happened with SETI 02+14a, a radio whisper that drifted into our telescopes in 2003 from the direction of the constellation Pisces. Unlike the jarring intensity of the WOW signal or the repeating fireworks of FRB 121102, this one was subtle, almost shy, a faint, persistent hum at a frequency of around 1042 MHz. But what made it extraordinary was how it seemed to drift. Normally, cosmic radio sources stay locked to a specific frequency, but SETI 02+14 slowly shifted over time, as if whatever produced it was moving and fast. The leading natural explanation points to pulsars, rapidly spinning neutron stars that emit beams of radio waves like cosmic lighthouses. If one were wobbling slightly, a phenomenon known as precession, its signal could appear to drift. But here's the catch: the observed drift rate was far steeper than any known pulsar's wobble. To match it, a pulsar would need to be tumbling wildly, something no known astrophysical process should cause. Another theory suggests interference from Earth-based sources, like a satellite or aircraft, but the signal's hydrogen line frequency, a band often considered ideal for interstellar communication, makes that feel oddly coincidental. Then there's the more provocative idea: could this be a transmission from a planet orbiting a distant star? The drift could hint at a transmitter placed on a rapidly rotating world, its motion tugging the signal's frequency like the Doppler effect of a passing ambulance siren. If true, the math suggests the planet would need a day shorter than Earth, spinning at a dizzying pace. But even then, the signal's weakness raises questions. Would an advanced civilization send a message so faint it barely registers? Or was it never meant for us at all, a cosmic broadcast aimed elsewhere, brushing past Earth by chance? The frustrating beauty of SETI-02 plus 14 lies in its ambiguity. Unlike clearer cosmic oddities, it lingers in the gray zone, too strange to dismiss, yet too faint to confirm. Despite years of scrutiny, no one's ever detected it again, leaving us with only theories and a lingering sense of wonder. Whether it's a fluke of physics or a fleeting hello from the void, this quiet signal reminds us that sometimes the universe's most intriguing messages aren't shouts, they're whispers, barely heard, begging us to lean in closer. Before fast radio bursts had a name, before astronomers even knew to look for them, a single anomaly in old data rewrote the rules of cosmic phenomena. In 2007, astrophysicist Duncan Lorimer and his student David Narkevic were sifting through archival recordings from the Parkes Radio Telescope in Australia when they stumbled upon something extraordinary. A 5-millisecond spike of energy so powerful, it blazed brighter than entire galaxies. This was the Lorimer burst, the first fast radio burst ever identified, and it defied every expectation. What made it so baffling wasn't just its intensity, equivalent to the sun's total energy output over 30 days packed into a flicker of time, but where it seemed to come from. The signal's dispersion, a telltale smear of radio waves caused by traversing cosmic plasma, suggested it had traveled 3 billion light-years, yet efforts to trace its origin led to nothing. No visible galaxy, no stellar remnant, not even a wisp of gas where such an explosion should have left scars. It was as if the universe had snapped its fingers, releasing a burst of energy with no apparent source. Theories erupted almost as violently as the burst itself. One leading idea points to blitzars, hypothetical events where a supermassive neutron star collapses into a black hole. Picture a dying star so dense, a teaspoon of its material would weigh 1 billion tons. If such an object's magnetic field suddenly destabilized, it could unravel in a catastrophic instant, converting its immense rotational energy into a fireball of radio waves. Alternatively, the burst could stem from 2 neutron stars spiraling into each other, their final embrace rippling space-time and hurling out a shockwave of radiation. But here's the twist. Later studies revealed that the Lorimer burst wasn't alone. Hidden in other telescope archives were similar anomalies previously dismissed as glitches. This realization birthed an entire field of study, transforming what seemed like a one-off event into a cosmic pattern we're still struggling to decode. Whether these bursts are the death cries of exotic stars or something even more mysterious, their discovery proved one thing: the universe is far more dynamic and far more unpredictable than we ever imagined. In 1974, scientists at the Arecibo Observatory aimed humanity's most powerful radio telescope at a star cluster 25,000 light-years away and broadcast a carefully crafted message into the void, a string of binary code encoding everything from our DNA structure to a crude image of a human figure. It was less an attempt at contact and more a symbolic gesture, a cosmic bottle tossed into the ocean. Then, 27 years later, something astonishing appeared. In August 2001, a crop circle near the Chilbolton Radio Telescope in England displayed what looked like a direct response, a near-identical format but with eerie alterations. The human figure became a large-headed alien silhouette, the DNA strand twisted into a triple helix, and our solar system's diagram now featured a shifted planetary arrangement, including an emphasized 5th planet. The timing and precision were uncanny, almost too perfect. At first glance, the so-called Arecibo response seemed like the stuff of science fiction dreams. But skeptics quickly raised red flags. Crop circles, no matter how intricate, are notoriously human-made, with teams of artists publicly claiming responsibility for hundreds of designs over the years. The Chilbolton Formation appeared in a field beneath an active radio telescope, a conspicuous location for anyone wanting to stage an interstellar conversation. Even the signal's alleged content raised eyebrows. A triple helix DNA structure contradicts known biochemistry, and the modified solar system map included inaccuracies, like a planet positioned where none exists in our actual cosmic neighborhood. Yet the mystery deepens when you consider the logistics. Creating such a complex design overnight without detection would require extraordinary coordination. The binary code was flawlessly aligned with the original Arecibo format, a detail that would demand not just artistic skill, but advanced knowledge of the 1974 transmission. Could it have been an elaborate hoax by someone with insider expertise? Possibly. But why go to such lengths for a prank that wouldn't yield fame or profit? The most tantalizing question isn't whether the Arecibo response was real. It's what it would mean if it were. A genuine reply would imply a civilization not only capable of decoding our message within decades, but also physically reaching Earth to imprint their answer in a wheat field. That level of technology defies our understanding of physics, suggesting methods of travel or communication far beyond anything we've theorized. Or perhaps the message wasn't a literal response but a cosmic coincidence, an unintended alignment of human creativity and the universal longing for connection. Whether art or artifact, the Arecibo response endures as a cultural touchstone, blurring the line between hoax and hope. It challenges us to ask how we'd recognize a true signal amid the noise of our own imagination, and whether we're truly ready for the answer. In 2020, astronomers with the Breakthrough Listen project detected something extraordinary, a narrowband radio signal at 982 MHz emanating from Proxima Centauri, the closest star system to our own. Dubbed BLC-1, this signal sent waves of excitement through the scientific community. Here was a whisper from just 4.2 light-years away, in the habitable zone of a star we know hosts at least one rocky planet. The signal's frequency appeared clean, devoid of the usual cosmic static, and it drifted in a way that suggested movement, perhaps a transmitter on a rotating planet. For a brief, thrilling moment, it seemed humanity might be on the verge of answering its oldest question: are we alone? Initial observations only deepened the intrigue. The signal persisted during multiple observations, ruling out a passing satellite or aircraft. It originated from a region of space where no human-made technology should be operating, and its frequency fell within a relatively quiet band, unlikely to be contaminated by terrestrial interference. Researchers even ruled out known astrophysical sources like flaring stars or pulsars. The more they scrutinized BLC-1, the more it defied conventional explanations. Could this finally be the evidence we've spent decades searching for? But science thrives on skepticism, and as teams dug deeper, cracks began to appear. Further analysis revealed that the signal's drift rate, the subtle shift in frequency caused by relative motion, didn't quite match what you'd expect from a planet orbiting Proxima Centauri. Then came the clincher. When researchers pointed telescopes back at the star, the signal was gone. No repetition, no consistency. The final blow landed when they discovered that similar signals could be replicated by common electronic interference, like poorly shielded consumer devices. By 2021, the consensus was clear. BLC-1 wasn't an alien hello, it was likely a human-made artifact, a false positive mimicking the very thing SETI scientists hoped to find. Yet BLC-1 wasn't a failure. It taught the scientific community invaluable lessons about the challenges of hunting for extraterrestrial signals in an increasingly noisy world. Modern Earth is awash in radio pollution, Wi-Fi, satellites, even microwaves can produce signals that mimic cosmic phenomena. The episode underscored the need for stricter verification protocols, like requiring signals to appear in multiple telescopes across different locations to rule out local interference. It also highlighted how even the most promising detections demand relentless scrutiny, a reminder that extraordinary claims require extraordinary evidence. What lingers from BLC-1 isn't disappointment but curiosity. Proxima Centauri remains a prime target in the search for life, with its Earth-sized planet Proxima b orbiting within the star's habitable zone. If a signal like this could spark such intense debate from so close, what might we find when we train our telescopes on the next star and the next? The universe is vast and the search has only just begun. Nothing reshaped the study of fast radio bursts quite like the Canadian Hydrogen Intensity Mapping Experiment, better known as CHIME. This sprawling, half-pipe-shaped radio telescope in British Columbia wasn't even designed to hunt for FRBs, yet it became the most prolific FRB detector in history, uncovering hundreds of these fleeting cosmic flashes. What set CHIME apart was its ability to scan enormous swaths of sky simultaneously, catching bursts other telescopes might miss. And what it found turned the field on its head. FRBs weren't the rare, exotic oddities we once thought. They were happening all the time, all across the universe, some repeating, some vanishing forever, each one a fresh puzzle waiting to be solved. The real game-changer came when CHIME began spotting patterns. In 2019, it detected the second known repeating FRB, a signal dubbed FRB 180916 that erupted from a spiral galaxy 500 million light-years away. Unlike the chaotic randomness of earlier bursts, this one had a rhythm, a 16-day cycle of activity, with bursts clustering over 4 days before falling silent for 12. That kind of predictability hinted at an orbital origin, perhaps a neutron star swinging around a companion star, its outbursts flaring like clockwork whenever its magnetic field tangled with stellar winds. But CHIME discoveries didn't stop there. Some bursts arrived with a strange double-peaked structure, as if the signal had echoed off some invisible cosmic barrier. Others showed Faraday rotation, a twisting of radio waves that suggested they'd passed through incredibly dense magnetic fields. These details painted a picture of environments far more extreme than anything in our own galaxy, places where the laws of physics might bend under conditions we can scarcely replicate. One radical theory points to cosmic strings, hypothetical, thread-like defects in space-time left over from the Big Bang. If these relics exist, their vibrations could release titanic bursts of energy as they snap or interact, creating FRBs in the process. It's a wild idea, but it would explain why some bursts seem to come from nowhere with no visible source. Alternatively, FRBs might be the death throes of primordial black holes, evaporating in flashes of Hawking radiation after eons of lurking unseen. What makes CHIME FRBs so compelling isn't just their mystery, it's how they've forced us to rethink the universe's extremes. Every new detection chips away at our assumptions, revealing a cosmos far more dynamic and violent than we ever imagined. Whether they are born from collapsing stars, colliding dimensions, or something even stranger, one thing's clear: these bursts aren't just cosmic static. They're the universe's way of reminding us how much we still have left to discover. In 2015, something unusual flickered across the screens of the Ratan 600 radio telescope in Russia, a signal so compelling it instantly reignited debates about intelligent life beyond Earth. Detected in the direction of HD 164595, a Sun-like star 94 light-years away, this burst of radio waves stood out for one striking reason. It pulsed at a frequency of 11 GHz, a range largely devoid of natural cosmic noise. Typically, such clean, narrowband signals are the hallmark of human-made technology, satellites, radar, or communication arrays. But this one came from deep space, with none of the telltale interference or drift you'd expect from local sources. For a brief moment, it seemed we might have stumbled onto evidence of another civilization reaching out. The star system itself added fuel to the speculation. HD 164595 isn't just any star. It's a near twin to our Sun, roughly the same size, temperature, and age. Orbiting it is a confirmed gas giant, and while no Earth-like planets have been found yet, the conditions seemed plausible for life to arise elsewhere in that system. When the signal was detected during a survey of stellar systems, the team's initial excitement was palpable. Could this finally be the breakthrough SETI researchers had spent decades hoping for? But science demands skepticism, and counterarguments emerged quickly. Critics pointed out that the signal appeared only once despite repeated follow-up observations, a red flag for any potential extraterrestrial transmission. Advanced civilizations, the logic goes, wouldn't send a single, fleeting hello. They'd either repeat the signal or make it continuous. Then there's the issue of contamination. 11 gigahertz is a frequency used by military and scientific equipment on Earth, raising the possibility that the signal was a stray whisper from our own planet, bouncing off space debris or atmospheric layers in a way that mimicked a distant origin. Even the telescope's design came under scrutiny. Rattan 600 uses a unique, ring-shaped array that can sometimes produce false positives, especially when dealing with faint signals near the edge of detection. Yet the most compelling natural explanation might lie in a phenomenon called stellar scintillation. Just as Earth's atmosphere makes stars twinkle, interstellar plasma can bend and amplify radio waves, causing distant natural sources like quasars or pulsars to momentarily flare into detectability. If a previously unnoticed quasar happened to align perfectly with HD 164595's position, its signal could have been magnified just long enough to mimic an artificial transmission. It wouldn't be the first time cosmic illusions fooled us. What makes the Rattan 600 signal so fascinating isn't its resolution ultimately. It was likely instrumental or environmental noise, but how perfectly it encapsulated the challenges of the search for extraterrestrial intelligence. Even with cutting-edge technology, distinguishing a true cosmic hello from the universe's endless background chatter remains a monumental task. Every ambiguous signal forces us to refine our methods, sharpen our tools, and confront the humbling reality that the universe is always more inventive than our assumptions. Whether it's a glitch, a quirk of physics, or something waiting to be rediscovered, one thing's certain: the hunt is far from over. The star HD 164595 was already intriguing long before any mysterious signals entered the picture. A near-mirror image of our Sun located 94 light-years away in the constellation Hercules, complete with at least one known gas giant orbiting it. But in May 2016, this unassuming star suddenly became the center of scientific debate when Russian astronomers picked up an unusual radio burst from its direction. Lasting just a few seconds, the signal packed a powerful punch at 11 gigahertz, a frequency suspiciously absent from most natural cosmic phenomena. Clean, narrowband, and strikingly artificial in appearance, it was exactly the kind of radio whisper SETI researchers had spent decades hoping to find. Initial reactions ranged from cautious optimism to outright excitement. Here was a signal matching the profile of potential extraterrestrial technology, coming from a star system that checked all the boxes for habitability. Unlike chaotic cosmic static or the scattered emissions of distant quasars, this pulse was concentrated and deliberate, almost engineered. Some researchers even noted its frequency fell within what's known as the water hole, a quiet band of the radio spectrum between hydrogen and hydroxyl wavelengths where advanced civilizations might logically transmit messages. The implications were staggering. Had we just intercepted a cosmic SOS, or even an intentional hello from a civilization orbiting a sun nearly identical to our own? But in science, extraordinary claims require extraordinary evidence, and the HD 164595 signal quickly faced intense scrutiny. For starters, despite repeated follow-up observations by telescopes worldwide, the signal never reappeared. That's problematic for any supposed alien transmission. Any society capable of interstellar communication would presumably repeat its message or leave it broadcasting continuously. Then came the interference argument. 11 gigahertz is heavily used by military radar, satellite communications, and even microwave ovens here on Earth. The signal's artificial perfection suddenly seemed less like proof of extraterrestrial intelligence and more like a stray radio wave bouncing off space debris or atmospheric layers. Even the natural explanations had twists. One compelling theory suggests the signal might have been amplified by interstellar scintillation, a phenomenon where distant radio sources flicker in brightness as their waves pass through turbulent clouds of cosmic plasma. Imagine a quasar or pulsar normally too faint to detect, its signal magnified briefly like sunlight through a magnifying glass, only to fade back into obscurity. If such an object happened to lie in the same line of sight as HD 164595, it could have masqueraded as a transmission from the star itself. What makes this signal so fascinating isn't its resolution. Most experts now agree it was likely interference or a cosmic illusion, but how neatly it encapsulates the needle in a haystack challenge of searching for extraterrestrial intelligence. Even with our most advanced tools, distinguishing a genuine alien broadcast from the universe's endless noise requires more than just a single, fleeting anomaly. It demands repeatability, localization, and patterns that defy natural explanation. The HD 164595 episode reminded scientists that the universe is full of false alarms, but it also sharpened their strategies for the next potential detection. After all, if we're ever going to find definitive proof we're not alone, we'll need to separate the cosmic signals from the noise with flawless precision. And that's a puzzle as thrilling as the search itself. Of all the cosmic oddities we've encountered, few are as stubbornly mysterious as Tabby's star. Officially known as KIC 8462852, this unassuming flicker of light in the constellation Cygnus first made headlines in 2015 when astronomers noticed something deeply unusual. Its brightness wasn't just fading slightly, as stars sometimes do. It was plunging in erratic, dramatic dips, sometimes by as much as 22%. That's like watching a 100-watt light bulb suddenly dim to 78 watts for no apparent reason, then bounce back unpredictably. No known natural phenomenon, not planets, not comets, not even internal stellar processes could fully explain such extreme, irregular dimming, and that's when the speculation really took off. Could we be looking at something artificial, a vast alien megastructure perhaps built to harness the star's energy? The leading natural theory points to swarms of orbiting dust or cometary fragments. Imagine a star surrounded by a colossal debris field, thick clouds of fine particles or shattered icy bodies passing in front of it, blotting out its light in uneven clumps. Observations eventually detected traces of such dust in the star's light spectrum, lending some credence to this idea. But here's the catch: the dust alone doesn't account for the sheer scale of the dimming. Ordinary dust scatters light predictably. Tabby's star's dips are anything but predictable. Some last for days, others for weeks, with no discernible pattern. Even more baffling, long-term studies revealed the star's overall brightness has been steadily declining by as much as 3% per century. Stars this age simply don't behave this way naturally. That's where the more radical hypotheses enter the scene. The idea of a Dyson swarm, a hypothetical network of energy collecting satellites or panels encircling a star, was first proposed by physicist Freeman Dyson in the 1960s. If an advanced civilization had constructed something like this around Tabby's star, the irregular dimming could reflect ongoing construction, repairs, or even varying energy demands. It's a thrilling thought, but scientists caution against jumping to conclusions. The universe is full of surprises, and alien megastructures should always be the last resort explanation, not the first. Yet what makes Tabby's star so compelling isn't just the wild theories it inspires, it's the way it refuses to fit neatly into any box. Even after years of study, no single explanation covers all the anomalies. Some researchers suggest chaotic magnetic activity or a recent planetary collision. Others propose a family of super-sized comets, though their sheer number would defy anything in our solar system. Then there's the unsettling possibility we're seeing something entirely new, a stellar phenomenon we haven't even begun to classify. Perhaps the most fascinating aspect of this mystery is what it says about our own curiosity. Tabby's star doesn't just challenge our understanding of stars, it forces us to confront how we interpret the unknown. Every time we think we've pinned it down, it slips away, reminding us that the cosmos still holds puzzles we can't yet solve. Whether it's dust, debris, or something far more extraordinary, one thing's certain: this star isn't done surprising us, and that's what keeps astronomers and the rest of us staring at the sky, waiting for the next clue to reveal itself. Deep in the farmlands of New South Wales, Australia, the Parkes radio telescope, affectionately nicknamed the Dish, has spent decades eavesdropping on the universe. Its towering white bowl has captured everything from the moon landings to pulsars, but some of its most perplexing recordings aren't cosmic at all. They're the bizarre bursts known as peritons, signals that initially seem to defy classification. Unlike the distant crackle of fast radio bursts or the steady pulse of neutron stars, these bursts had a strange signature, scattered across multiple frequencies, as if the signal had been smeared across the sky. For years, they haunted astronomers, blurring the line between celestial phenomena and something far closer to home. The mystery deepened when researchers noticed a peculiar pattern. Peritons only appeared during business hours. That's not how astrophysics works. Cosmic signals don't punch a time clock. The realization sparked a hunt for terrestrial culprits, and in 2015, the answer turned out to be laughably mundane: microwave ovens. Specifically, old ovens in the observatory's staff kitchen. When opened mid-cycle, they emitted a burst of radiation that ricocheted off the telescope's metal structures, creating a signal that mimicked a cosmic event. It was a humbling reminder that even our most advanced tools can be fooled by the quirks of everyday life. But not every odd signal at Parkes has a kitchen appliance to blame. In 1998, the telescope picked up a series of ultra-short, ultra-bright pulses later dubbed the Lorimer burst, the first recognized fast radio burst. Unlike peritons, this signal came stamped with the unmistakable fingerprint of intergalactic travel, its waves stretched by plasma across billions of light years. Then there's the wow signal predecessor, a one-off burst detected in 1977 that shared eerie similarities with its more famous cousin, right down to its hydrogen line frequency. What makes Parkes such a hotspot for cosmic mysteries isn't just its sensitivity, it's its location. Situated in the southern hemisphere, it scans skies less cluttered by human radio interference, offering a clearer window into the universe's whispers. Yet that same isolation makes it vulnerable to local oddities, from grazing sheep tripping electrical fences to passing aircraft reflecting stray signals. Sorting the cosmic from the terrestrial is a constant battle, one that's reshaped how astronomers vet potential discoveries. The lesson of Parkes isn't just about faulty microwaves or sheep-induced static, it's about the delicate dance of discovery. Every signal, no matter how promising, must survive a gauntlet of skepticism, because in the search for the extraordinary, the universe's greatest trick might be hiding its wonders in the noise of the ordinary. And sometimes, the most important breakthroughs begin with realizing you've been chasing a microwave all along. Hidden within the tangled heart of our galaxy, where stars crowd together like fireflies in a jar, lies a signal that refuses to play by the rules. Known as Glimpse C01, this enigmatic radio whisper originates from one of the Milky Way's most densely packed stellar neighborhoods, a globular cluster called Glimpse C01, located roughly 10,000 light-years away. What makes this signal so baffling isn't just where it's coming from, but how it behaves. Unlike the predictable pulses of a neutron star or the erratic bursts of a magnetar, this emission flickers on and off in a pattern that defies every known category of cosmic radio source. It's too sporadic to be a pulsar, too structured to be random noise, and too persistent to dismiss as a glitch. At first glance, globular clusters seem like unlikely places for mysterious signals. These ancient swarms of stars, bound together by gravity, are typically devoid of the turbulent gas and young stellar objects that produce dramatic radio emissions. Yet Glimpse C01 signal emerged from this seemingly quiet region, and its properties left astronomers scratching their heads. The signal's frequency drifts slightly over time, a trait often seen in objects moving at high speeds like orbiting planets or binary stars. But here's the twist: the drift rate doesn't match any known orbital mechanics in the cluster. If it's a natural object, it's moving in a way that challenges our understanding of celestial motion. One leading theory points to an elusive class of objects called ultra-long period magnetars. These are neutron stars with magnetic fields so intense they occasionally unleash colossal bursts of energy. But unlike regular magnetars, they operate on a much slower timescale, sometimes flaring only once every few years. If such an object lurks in Glimpse C01, its sporadic eruptions could explain the signal's irregular appearances. Another possibility involves a black widow pulsar, a rapidly spinning neutron star that's slowly devouring a smaller companion star. As the pulsar's intense radiation strips material from its neighbor, the resulting turbulence could generate chaotic radio emissions. Yet there's a more tantalizing, if controversial, angle. Some researchers have floated the idea that Glimpse C01 signal could be artificial. Globular clusters are ancient, stable environments, perfect places for long-lived civilizations to establish beacons or relays. The signal's unusual drift might reflect a transmitter on a planet with a slow, wobbling rotation, or even a megastructure adjusting its position. It's a fringe hypothesis, but it underscores how little we truly understand about the signal's origin. What makes Glimpse C01 so compelling isn't just the lack of answers, it's the way it forces us to question our assumptions. Every time we think we've pinned it down, the signal slips through our fingers, revealing gaps in our knowledge of stellar behavior and the extremes of physics. Whether it's a dying star's last gasps, a cosmic collision we can't yet imagine, or something even more extraordinary, one thing's certain: the universe still holds puzzles that defy our best tools and brightest minds. And sometimes the most profound discoveries begin with a signal that simply refuses to make sense. For decades, the Vela pulsar has been one of the most reliable timekeepers in the cosmos. A spinning neutron star beaming radio waves across the galaxy like a celestial lighthouse with a rhythm so precise it rivals atomic clocks. But in 1998, astronomers noticed something unsettling. This cosmic metronome had faltered. Without warning, its spin rate abruptly changed, sending shockwaves through the astrophysics community. This wasn't just a minor hiccup. It was a glitch, a sudden speed-up in rotation so dramatic it defied conventional models of how pulsars behave. And if something as fundamental as pulsar spin could be thrown off course, what did that mean for our understanding of these stellar corpses? Theories poured in, with most pointing to the pulsar's unfathomably dense interior. Picture a sphere just 12 miles across, yet weighing more than our sun, a place where matter is crushed into exotic states beyond anything we can recreate on Earth. Under such extreme conditions, the star's crust isn't just solid. It's a super-dense crystalline lattice under immense strain from the star's rapid spin and monstrous magnetic field. When that stress becomes too much, the crust might suddenly crack, a starquake, releasing energy equivalent to millions of atomic bombs. This violent adjustment could explain the glitch, as the star's outer layers briefly detach from its superfluid core, then recouple at a faster rate. But the Vela pulsar wasn't done surprising us. In 2016, it glitched again, this time with an added twist. Alongside the rotational speed-up, its radio emissions flickered unpredictably, as if the star's magnetic field had momentarily twisted into a new configuration. That kind of magnetic turmoil isn't supposed to happen in such an ordered system. Pulsars are meant to be stable, their magnetic fields locked into rigid alignment with their spin axes. Yet here was Vela, behaving more like a temperamental engine sputtering under strain. Some researchers now suggest these events could be tied to vortices in the pulsar's superfluid core, whirlpools of ultra-dense matter that occasionally break free and surge outward, dragging the star's rotation along with them. Then there's the wildcard theory. What if these glitches aren't internal at all? A handful of scientists speculate that passing dark matter clouds or even microscopic primordial black holes could interact with the pulsar's structure, delivering an invisible kick that disrupts its spin. It's a fringe idea, but in the absence of definitive answers, even radical possibilities deserve consideration. What makes the Vela pulsar so fascinating isn't just its anomalies, it's the way they force us to rethink the extremes of physics. Every glitch is a snapshot of conditions we can't replicate, offering clues about matter at densities where the rules of quantum mechanics and gravity collide. Whether it's quakes, magnetic upheavals, or something even stranger, each disruption peels back another layer of mystery, reminding us that even the universe's most predictable objects can still surprise us. And in those surprises lie the next great leaps in our understanding. In the early 1970s, astronomers tuning their instruments to the cosmos stumbled upon a rhythmic enigma, Hercules X1, an X-ray source pulsing with eerie precision like a galactic heartbeat. Every 1.24 seconds, like clockwork, a burst of high-energy radiation surged from this distant binary system, located over 20,000 light-years away in the constellation Hercules. But what made this signal truly bizarre wasn't just its regularity. It was the way it seemed to defy the known physics of celestial objects. Normal stars don't pulse in X-rays. Planets don't flicker with such machine-like consistency. Hercules X1 was something entirely different, a cosmic oddity that would redefine our understanding of the universe's most extreme environments. The key to the mystery lay in the system's composition. Hercules X1 isn't a single star, it's a dance of two objects locked in a gravitational embrace. On one side, a massive blue supergiant star, dozens of times heavier than our Sun. On the other, an invisible companion so dense it warps space-time around it, a neutron star. As the supergiant's stellar winds pour material onto its tiny, ultra-dense neighbor, that matter doesn't just fall gently, it spirals inward at nearly the speed of light, forming a searing hot accretion disk. When those superheated particles slam into the neutron star's surface, they release torrents of X-rays. But here's the puzzle. The 1.24-second pulses don't come from the disk itself. They're the neutron star's rotation, sweeping its magnetic poles across our line of sight like a lighthouse beam, each pass delivering another burst of radiation. Yet even this explanation leaves gaps. Why does the signal's intensity sometimes waver unpredictably? For decades, astronomers noted strange glitches where the pulses arrived slightly early or late, tiny timing deviations that shouldn't occur in such a stable system. One theory suggests the neutron star's crust might occasionally fracture under unimaginable strain, its surface shifting like tectonic plates in a starquake. Another possibility points to clumps of material in the accretion, disk-dense knots of gas that briefly disrupt the flow of matter onto the neutron star, throwing off its rhythm. Then there's the system's 35-day cycle, where the X-rays periodically vanish altogether. Some researchers argue this could be caused by a warped, precessing disk that temporarily obscures our view, while others speculate about magnetic field interactions twisting the disk into strange new shapes. The most tantalizing question of all is what we're not seeing. Neutron stars are laboratories of extreme physics, their interiors likely packed with exotic states of matter, quark-gluon plasma, superfluids, or even stranger configurations. Hercules X1's pulses might carry encoded clues about these unknown materials if only we could decipher them. And let's not forget the broader implications. Systems like this are cosmic factories, forging heavy elements like gold and platinum in their violent interactions. Every pulse is a reminder that the universe's most mysterious signals aren't just curiosities, they're keys to understanding where the very building blocks of our world come from. What keeps Hercules X1 captivating isn't just the answers it's given us, it's the questions that still linger. After half a century of study, this rhythmic X-ray beacon continues to challenge our models, pushing the boundaries of what we thought possible. Whether it's revealing the secrets of ultra-dense matter or hinting at unseen dynamics in accretion disks, one thing's certain: the universe's most fascinating signals are often the ones that refuse to behave. In the midst of the Cold War space race, when humanity's gaze was fixed firmly on the stars, astronomers detected something that sent shockwaves through the scientific community: a series of erratic, powerful flares emanating from an object called CT-102. Discovered in 1963 by Russian scientists using the Crimean Astrophysical Observatory, this mysterious radio source didn't behave like anything else in the known universe. Its signal strength fluctuated wildly, sometimes surging by factors of hundreds in mere days, far too rapid for typical cosmic phenomena. The erratic nature of these bursts sparked immediate speculation. Were we witnessing natural stellar processes or something far more deliberate? At the time, quasar research was still in its infancy. These incredibly luminous yet distant objects were only just being recognized as active galactic nuclei powered by supermassive black holes. But CT-102's behavior seemed extreme even for a quasar. The fluctuations were so intense that Soviet astrophysicist Nikolai Kardashev publicly entertained the idea that the signal might be artificial, a beacon from a civilization harnessing energy on a previously unimaginable scale. The notion made headlines worldwide, fueling both scientific debate and public fascination with the possibility of extraterrestrial intelligence. The truth, when it emerged, was no less extraordinary. Further observations revealed CT-102 as one of the most luminous quasars ever detected, located approximately 8 billion light-years away. Its dramatic flares weren't messages from aliens, but violent outbursts from materials swirling near the event horizon of a supermassive black hole billions of times the mass of our Sun. As gas and dust spiraled inward at relativistic speeds, magnetic fields twisted and snapped like cosmic rubber bands, accelerating particles to near-light velocity and generating those erratic radio waves. What made these flares unique was their scale and variability. Unlike slower, more predictable quasar emissions, CT-102's outbursts occurred on timescales of days, a clue to the astonishingly compact region where they originated. The energy required for such rapid fluctuations suggested a central engine no larger than our solar system, packing the power output of entire galaxies into a space unimaginably small by cosmic standards. The legacy of CT-102 isn't just about solving a mystery, it reshaped how we study the universe. This episode taught astronomers the importance of skepticism when confronting the unknown, while simultaneously expanding our understanding of quasars' extreme physics. It also highlighted how easily natural phenomena, when pushed to cosmic extremes, can mimic the signatures we associate with intelligence. Today, as we detect ever more distant and energetic objects, the lessons of this 60s enigma remind us that the universe's most awe-inspiring wonders often lie not in alien messages, but in the raw, unfiltered power of nature itself. Back in 1967, a young astrophysicist named Jocelyn Bell Burnell was reviewing data from a new radio telescope in Cambridge when she spotted something bizarre. A series of sharp, precise pulses arriving every 1.337 seconds with clockwork regularity. The signal, originating from a patch of sky near the constellation Vulpecula, was so unnervingly consistent that her team jokingly labeled it LGM-1, short for Little Green Men. At a time when the search for extraterrestrial intelligence was gaining momentum, It seemed plausible, even thrilling, that humanity's first contact might come not as a message, but as a cosmic metronome ticking across the void. The truth was far more extraordinary. What Bell Burnell had discovered later, named PSRB 1919+21, wasn't alien in origin, but it was revolutionary. The first known pulsar, a rapidly spinning neutron star emitting beams of radiation from its magnetic poles. Imagine the collapsed core of a massive star, heavier than our sun yet just 12 miles across, spinning faster than a kitchen blender. As it rotates, its lighthouse-like beams sweep across space, and when aligned with Earth, we detect those rhythmic pulses. The sheer precision of these signals, accurate to within a billionth of a second, rivaled the best atomic clocks on Earth, revealing a new class of celestial object that defied prior assumptions about stellar evolution. Initially, the discovery sent shockwaves through the astronomy community. Neutron stars had been theorized since the 1930s, but their existence was considered speculative, almost fantastical. The idea that a stellar corpse could pack such mass into such a tiny volume, with gravity so intense that protons and electrons merge into neutrons, seemed like science fiction. Yet here was PSRB 1919+21, offering irrefutable proof. Its pulses weren't just a curiosity. They were glimpses into the physics of matter under conditions so extreme they can't be replicated in any laboratory. What makes this signal so pivotal isn't just its scientific impact, it's the cultural shift it triggered. Before pulsars, astronomers had never encountered natural signals so artificial seeming in their regularity. The experience taught researchers a humbling lesson. The universe often outstrips our imagination, producing phenomena that blur the line between natural and engineered. Today, we know of thousands of pulsars, each with its own rhythm, from millisecond pulsars spinning hundreds of times per second to glitching pulsars that occasionally stumble like a skipping record. But PSRB 1919+21 remains the archetype, the first heartbeat in humanity's discovery of the cosmos' hidden cadences. The story of LGM-1 also underscores how preconceptions shape discovery. Bell Burnell nearly dismissed the signal as instrument noise, and even her supervisor, Anthony Hewish, initially attributed it to terrestrial interference. It was her persistence that uncovered the truth, a reminder that breakthroughs often lie just beyond the edge of what we think we know. Whether as a cautionary tale about jumping to alien conclusions or a testament to the universe's capacity for wonder, this first pulsar signal remains one of astronomy's most transformative moments. And it all began with a rhythm so perfect it made scientists wonder if someone or something was tapping back. In 2015, headlines around the world blared an electrifying possibility: astronomers had detected a signal from the Andromeda galaxy, our closest galactic neighbor. Originating from the direction of Messier 31, this burst of radio waves sparked immediate excitement. What set it apart wasn't just its apparent extragalactic origin, but its uncanny resemblance to the kind of narrowband transmission an advanced civilization might produce. At a time when fast radio bursts were still poorly understood, the prospect of a deliberate signal from 2.5 million light-years away felt like science fiction becoming reality. The initial observations came from the Russian Academy of Sciences Ratan 600 telescope, the same instrument that later scrutinized the HD 164595 signal. This time, the frequency was even more suggestive, 11 GHz again, but with a stability so precise it seemed engineered. Unlike the chaotic static of natural cosmic sources, this emission held its frequency like a well-tuned radio station. Researchers scrambled to rule out local interference, checking satellites, military radar, and even atmospheric reflections. For a brief window, it seemed plausible that humanity had stumbled onto something historic, a whisper from another galaxy. But the euphoria was short-lived. When other radio telescopes worldwide trained on Andromeda, they found nothing. No matching signal, no repeating pattern, just the usual cosmic background hum. The discrepancy pointed to an uncomfortable truth. The original detection was likely terrestrial interference masquerading as a cosmic event. Further analysis revealed that the signal's characteristics aligned suspiciously with Soviet-era military radar systems, which sometimes leak radiation at similar frequencies. The final nail in the coffin came when astronomers realized the signal's apparent motion matched Earth's rotation, a telltale sign of a ground-based source. This episode underscores one of the greatest challenges in modern astronomy, the ever-increasing noise of our own civilization. From cell towers to satellite constellations, Earth's radio environment grows more crowded by the day, creating a minefield of false positives for researchers hunting cosmic signals. The Andromeda incident wasn't the first time interference fooled scientists, and it won't be the last. Yet it serves as a crucial lesson in rigor, the importance of cross-verification with multiple instruments, preferably on different continents, to weed out local artifacts. What lingers from this near miss isn't disappointment but fascination. The fact that a stray radar pulse could so convincingly mimic an alien transmission speaks volumes about the universe's capacity to surprise us. It also raises a provocative question. If we're this easily fooled by our own technology, how many genuine cosmic signals might we be dismissing as mere interference? The search continues with ever sharper tools and smarter filters, but one thing's certain: the line between noise and discovery remains razor thin. And sometimes the most valuable detections are the ones that teach us how much better we need to listen. Few signals have blurred the line between cosmic mystery and earthly interference as dramatically as the strange radio whisper from Ross 128. Detected in May 2017 by scientists at the Arecibo Observatory, this 11 GHz burst seemed to tick all the boxes for something extraordinary, a narrowband transmission from a quiet red dwarf star just 11 light-years away. Unlike the chaotic static of most stellar emissions, this signal appeared unnervingly artificial, drifting slowly in frequency as if emanating from a moving source. For 70 terrifying minutes, astronomers dared to wonder, had we finally intercepted a transmission from another civilization right next door? Ross 128 wasn't just any star. This dim red dwarf hosts at least one known rocky planet orbiting snugly within its habitable zone, a world where liquid water could theoretically pool on the surface. The signal's frequency only deepened the intrigue. 11 GHz sits in a relatively quiet stretch of the radio spectrum, a sweet spot where cosmic noise fades and deliberate transmissions might logically be placed. Even more compelling, the signal appeared only when telescopes pointed at Ross 128, vanishing when aimed at neighboring stars. For a brief window, it felt like the universe had handed us a smoking gun. But science doesn't rush to conclusions. The Breakthrough Listen team quickly mobilized, scanning Ross 128 across multiple radio bands with unprecedented precision. What they found was equal parts relieving and deflating. The signal wasn't repeating. Worse yet, it bore the fingerprints of human technology, that telltale frequency drift. It matched the movement of geostationary satellites thousands of miles overhead. The final nail came when researchers realized similar signals appeared near other stars, always when satellites crept into the telescope's side lobes, their faint reflections mimicking cosmic transmissions. The culprit was likely a communication satellite, its signal bouncing off terrestrial structures or atmospheric layers in ways even seasoned astronomers hadn't anticipated. This episode wasn't just a false alarm, it was a masterclass in scientific humility. Ross 128 underscored how easily our own creations can masquerade as extraterrestrial contact, especially as Earth's orbital infrastructure swells with thousands of satellites. It also revealed a critical gap in SETI playbook, the need for real-time multi-telescope verification. Had this signal been detected a decade earlier, before the satellite boom, would we have dismissed it so quickly? The incident forced astronomers to refine their protocols, prioritizing simultaneous observations from distant locations to weed out interference at the source. Yet the Ross 128 signal's legacy isn't just about caution, it's about possibility. That brief flash of excitement reminded us that the nearest stars remain largely unexplored frontiers. Red dwarfs like Ross 128 outnumber Sun-like stars 10 to 1 in our galaxy, each a potential host for habitable worlds. And while this signal wasn't the one, its very ambiguity proves how close we might be to detecting something real. The next time a strange whisper drifts in from the cosmic neighborhood, we'll be ready not just to listen, but to truly understand. Deep in the heart of our galaxy, where stars crowd together in a dizzying cosmic dance, something strange flickers to life every 76 minutes. Known as GCRT J1745-3009, this enigmatic radio source sits just a degree from the Milky Way's core, pulsing with a regularity that defies easy explanation. Discovered in 2006 by astronomers sifting through archival data from the Very Large Array in New Mexico, this signal doesn't behave like any known celestial object. It erupts into existence for about 10 minutes longer than most transient bursts, yet far shorter than typical periodic sources before vanishing as suddenly as it appeared. What makes it truly bizarre is that these outbursts don't correspond to any visible object, leaving researchers staring at empty patches of sky where the radio waves insist something must be. Theories about GCRT J1745-3009 range from the plausible to the downright speculative. One leading idea points to a rare type of binary system, a pairing where a compact object like a neutron star or white dwarf orbits a cooler companion star. If material from the companion sporadically falls onto the denser object, it could trigger periodic bursts of radio emission. But here's the catch: no such binary has ever exhibited outbursts this brief or this regular. Another possibility involves magnetars, neutron stars with ultra-powerful magnetic fields, but their emissions typically span the electromagnetic spectrum, not just radio waves. GCRT's singular focus on radio frequencies makes it an oddity. Then there's the more exotic explanation, a quark star. This theoretical object represents what might happen when a neutron star collapses under its own gravity, crushing protons and neutrons into a soup of free quarks. The resulting body would be even denser than a neutron star, with properties we can only guess at. If quark stars exist, their rotation or magnetic reconnection events might produce the kind of transient radio bursts we see in GCRT. It's a tantalizing thought, but without direct evidence, it remains firmly in the realm of hypothesis. The mystery deepens when you consider the signal's location. The galactic center is a tumultuous place packed with black holes, swirling gas clouds, and gravitational chaos. Any object surviving there would face extreme conditions, tidal forces, radiation bombardments, and magnetic fields strong enough to distort atoms. Could GCRT be the remnant of a stellar collision, or perhaps a previously unknown class of object thriving in this hostile environment? The fact that similar signals haven't been detected elsewhere suggests it might be a product of its unique surroundings, a cosmic anomaly forged in the galaxy's most extreme crucible. What keeps astronomers returning to this 76-minute enigma isn't just the lack of answers, it's the way GCRT challenges our understanding of stellar life cycles. Most cosmic objects fit into neat categories: pulsars, quasars, supernova. GCRT refuses to conform, existing in a gray zone between established phenomena. Every time it flares up, it offers a fleeting opportunity to decode its secrets, a brief window into the universe's capacity for surprise. Whether it's a quark star's cry, a disrupted binary's death throes, or something entirely new, one thing's certain: the galactic center still holds mysteries we've only begun to glimpse. And sometimes the universe's most profound lessons come from the signals that refuse to be classified. While most telescopes strain to catch fleeting glimpses of fast radio bursts, Australia's ASKAP, the Australian Square Kilometre Array Pathfinder, turns them into a routine discovery. This sprawling network of 36 dish antennas scattered across the remote outback has revolutionized our understanding of these cosmic enigmas by doing something unprecedented, detecting FRBs not just one at a time but in bulk. Since its first major detection in 2017, ASKAP has expanded the catalogue of known fast radio bursts from a handful to hundreds, each one a tiny flare of mystery arriving from billions of light-years away. What makes these detections so transformative isn't just their quantity, it's their precision. Unlike earlier instruments that could only roughly trace a burst's origin, ASKAP unique phased array technology pinpoints locations to within a fraction of a degree, allowing astronomers to match signals with distant galaxies for the first time. The revelations have been staggering. ASKAP FRBs don't cluster in the chaotic star-forming regions we'd expect if magnetars were the sole culprits. Instead, many emerge from calm, aging galaxies, places where explosive stellar death should be rare. This mismatch has forced scientists to reconsider their assumptions. Could FRBs arise from quieter processes, like the slow-motion mergers of white dwarfs or the quiet collapse of ancient neutron stars into black holes? Even stranger, some ASKAP bursts arrive with a telltale smear of radiation, their waves stretched not just by the expansion of the universe but by traversing dense magnetic fields near their sources. These details hint at environments far more extreme than anything in our local cosmic neighborhood. One of the most tantalizing discoveries came in 2019, when ASKAP detected an FRB originating from a spiral galaxy remarkably similar to our own Milky Way. The burst's properties defied expectations. It was brighter and more complex than models predicted for such a common galaxy type. This raised a provocative question. Are FRBs not the exclusive domain of exotic, high-energy environments? Could they occur even in seemingly ordinary corners of the universe, hiding in plain sight? The implications ripple outward. If ordinary galaxies host these bursts, their true frequency might be far higher than we've dared to imagine, with thousands flashing across the cosmos every day unseen. Theories about ASKAP FRBs now span the spectrum from the mundane to the mind-bending. On one end, there's the Blitzar model neutron stars so massive their own gravity crushes them into black holes in a final brilliant flash. On the other, some researchers speculate about cosmic strings, hypothetical defects in spacetime left over from the Big Bang, vibrating like snapped guitar strings to release bursts of energy. Then there's the lingering, if unlikely, possibility of engineered signals. The burst's incredible brightness hints at energy harnessing beyond our comprehension, though most scientists caution that nature, when pushed to extremes, rarely needs artificial explanations. What sets ASKAP apart isn't just its technical prowess, it's the way these detections have turned FRBs from cosmic oddities into indispensable tools. By analyzing how the bursts interact with the intergalactic medium, astronomers can map the universe's invisible matter, tracing the distribution of atoms between galaxies. Each burst is like a flashlight beam passing through fog, illuminating the otherwise hidden structure of the cosmos. And with upgrades underway, ASKAP will soon detect even fainter bursts, probing deeper into the universe's youth when the first stars and galaxies ignited. The true power of these observations lies in their unpredictability. Every new FRB from ASKAP catalog chips away at our assumptions, revealing how little we truly understand about the universe's most energetic phenomena. Whether they're the echoes of dying stars, the tremors of spacetime itself, or something beyond our current physics, one thing's clear: the cosmos is speaking in bursts. And thanks to ASKAP, we're finally starting to listen. Tabby's star already captivated the world with its erratic dimming, but what if there's more to the story? In 2016, just as the astronomy community was grappling with the star's bizarre light fluctuations, another puzzle surfaced, faint radio signals reportedly emanating from its direction. Detected by the Green Bank Telescope in West Virginia, these whispers of electromagnetic energy weren't the structured bursts of a deliberate transmission, but they weren't typical stellar noise either. The signals clustered around frequencies between 1 and 10 gigahertz, a range where natural cosmic static usually fades, raising eyebrows among SETI researchers. Could this be another layer to the mystery evidence of something beyond mere cosmic dust or cometary swarms? The initial excitement was tempered by hard questions. Unlike the star's dramatic light dips, which were observed by multiple telescopes worldwide, these radio signals proved frustratingly elusive. Follow-up observations by the Allen Telescope Array in California failed to replicate the detections, casting doubt on whether the signals were truly extraterrestrial or even real. Interference from Earth-based sources like passing satellites or military radar couldn't be ruled out. Even the original Green Bank data showed inconsistencies, with signal strengths too variable to fit the profile of a steady beacon. If an advanced civilization were responsible, why would their transmissions flicker so unpredictably? Yet the possibility, however slim, refused to die. Some theorists pointed to the star's hypothetical megastructures as potential radio sources. Imagine a vast Dyson swarm under construction. Its chaotic assembly might scatter radio waves as workers, or machines adjusted solar collectors or relayed energy between components. Others proposed a less exotic but equally fascinating scenario: intense magnetic activity from Tabby's star itself. Young, magnetically hyperactive stars are known to produce radio flares, though none match KC 8462852's age or spectral type. Could this star harbor a rare, late-life magnetic tantrum, blurring the line between natural and artificial signals? The debate took a provocative turn when researchers analyzed the signal's bandwidth. Natural cosmic radio emissions tend to sprawl across frequencies like static on an untuned radio. These signals, by contrast, were relatively narrow, not quite the laser-like precision of a deliberate broadcast, but narrower than most stellar phenomena. That subtle distinction left room for speculation. Perhaps we weren't detecting a direct transmission, but leakage from power-hungry technology, something akin to Earth's own inadvertent radio pollution, radiating into space from our power grids and television stations. What makes this chapter of Tabby's star's saga so compelling isn't the certainty of a discovery, but the questions it forces us to confront. How would we distinguish between a cosmic coincidence and a genuine technosignature? Can nature, under extreme conditions, mimic the hallmarks of intelligence? For now, the radio signals remain an unsolved footnote, a tantalizing maybe in a mystery already overflowing with them. Whether they're artifacts of human error, stellar oddities, or something far more extraordinary, they underscore a humbling truth: the universe is full of whispers that dare us to listen more closely. And sometimes the most profound revelations begin with a signal we can't quite explain. In the vast tapestry of cosmic radio sources, few objects have rewritten the rules of astrophysics quite like 3C273. Discovered in 1963 by astronomer Martin Schmidt, this brilliant point of light didn't just defy expectations, it shattered them. Initially mistaken for a nearby star, its true nature emerged when Schmidt analyzed its spectrum and made a staggering realization. The object wasn't just distant, it was racing away from us at nearly 44,000 miles per second, its light stretched across billions of years by the expansion of the universe. This wasn't a star at all. It was the first identified quasar, a beacon of raw cosmic power so intense it outshines entire galaxies. What makes 3C273's signal so extraordinary isn't just its distance or brightness, it's the sheer violence of its emissions. Unlike the steady hum of pulsars or the erratic bursts of magnetars, quasars blast out energy across the entire electromagnetic spectrum, from radio waves to gamma rays, with enough force to light up the early universe like a flare in the cosmic dark. At their heart lies a supermassive black hole, billions of times heavier than our Sun, devouring matter at a ferocious rate. As gas and dust spiral inward, friction heats them to millions of degrees, creating an accretion disk so luminous it can be seen across the cosmos. The radio signals we detect are just the faint echoes of this maelstrom, the remnants of jets that shoot outward at nearly light speed, carving through intergalactic space like celestial blowtorches. Yet for all their destructive power, quasars like 3C273 are also cosmic time capsules. Because light takes time to travel, observing this quasar means peering back to an era when the universe was barely 2 billion years old, a time of chaos and formation when galaxies were still assembling themselves. The fact that such monstrous black holes existed so early challenges our models of cosmic evolution. How could structures this massive form so quickly after the Big Bang? Their very existence hints at gaps in our understanding, suggesting that black holes might grow through mechanisms we've yet to discover, or that the early universe was far more dynamic than we ever imagined. The lingering mystery of 3C273 isn't just about its origins, it's about the subtle irregularities in its signals. Some radio observations reveal faint flickers, periods where its output dips or spikes unpredictably. These aren't the clean pulses of a neutron star or the explosive randomness of a supernova. They're more like the guttering of a candle in a cosmic wind. One theory suggests these fluctuations come from clumps of matter falling haphazardly into the black hole, like logs tossed into a fire. Another posits that the jets themselves might be unstable, their magnetic fields knotting and unraveling as they stretch across light years. Then there's the tantalizing possibility that we're seeing light bent by intervening galaxies, their gravity warping the quasar's emissions like a funhouse mirror. What makes this first quasar so captivating isn't just its scientific impact, it's the way it blurs the line between the familiar and the unfathomable. To the unaided eye, 3C273 would appear as nothing more than a faint star in the constellation Virgo. Yet in reality, it's a cosmic hurricane, a storm of energy that defies human scales of time and space. Its radio whispers remind us that the universe is capable of violence and beauty on scales we're only beginning to comprehend, and that even after 60 years of study, the first quasar still has secrets left to reveal. For decades, fast radio bursts were the ultimate cosmic whodunit, powerful, unexplained flashes vanishing as quickly as they appeared with no obvious source. Then in April 2020, a breakthrough arrived from an unlikely corner of the Milky Way. Deep in the constellation Vulpecula, a city-sized stellar corpse known as SGR 1935+2154 suddenly erupted, sending shockwaves through the field of astrophysics. This wasn't just any outburst, it was the first time a magnetar, a highly magnetic neutron star, had been caught in the act of producing something eerily similar to an FRB right in our own galactic backyard. What set this event apart wasn't just the signal's intensity, though at milliseconds long it packed more energy than the Sun emits in 30 seconds, but its dual nature. As space telescopes like NASA's and Neil Gehrels Swift Observatory monitored the magnetar's X-ray flares, ground-based radio dishes simultaneously detected an accompanying radio burst with all the hallmarks of a genuine FRB. The implications were staggering. If magnetars could produce FRB-like signals even within our galaxy, perhaps these enigmatic cosmic flashes weren't exclusively extragalactic oddities after all. This was the smoking gun astronomers had sought for years, a direct link between a known object and one of the universe's most perplexing signals. The timing couldn't have been more poetic. Just months earlier, the same magnetar had entered a rare hyperactive state, its crust cracking under the strain of a magnetic field 1 trillion times stronger than Earth's. These starquakes likely triggered particle avalanches near the star's surface, accelerating electrons to near light speeds and generating the observed X-ray fireworks. But the radio burst was something new, a byproduct of those convulsions perhaps, or evidence of magnetic reconnection, events so violent they rippled through surrounding space like cosmic lightning. Either way, the detection suggested that magnetars, under the right conditions, could be cosmic double agents, quiet neutron stars one moment, FRB factories the next. Critically, SGR 1935 plus 2154's burst wasn't identical to extragalactic FRBs. It was thousands of times dimmer, a difference likely explained by its relatively close distance of 30,000 light-years. Scaling up its energy output to match the brightness of distant FRBs would require magnetars in far more extreme environments, places where magnetic fields might be amplified by surrounding debris or binary companions. This opened a Pandora's box of new questions. Are all FRBs produced by magnetars or just a subset? Could some bursts arise from entirely different mechanisms, like colliding neutron stars or evaporating primordial black holes? The fact that this galactic magnetar only produced one observable radio burst despite multiple X-ray flares hinted that FRB production might require a perfect storm of rare conditions. The discovery also forced a re-evaluation of how we classify cosmic signals. Before this event, FRBs were defined by their extragalactic origins, sudden, one-off flashes from billions of light-years away. Now the lines blurred. If magnetars in our own galaxy could produce FRB-like emissions, maybe the distinction between local and cosmic bursts was less about the mechanism and more about the observer's vantage point. This realization has already reshaped observational strategies, with astronomers now monitoring known magnetars for radio bursts that might have been previously overlooked. Perhaps most exciting is what this means for future research. With a confirmed galactic example to study, scientists can now dissect FRB-like signals with unprecedented precision, probing their polarization, spectral structure, and energy distribution in ways impossible for distant sources. Upcoming missions like the Square Kilometre Array, with its unparalleled sensitivity, could soon catch magnetars in the act more frequently, revealing whether SGR 1935 plus 2154's performance was a fluke or the first act of a broader cosmic play. The story of this magnetar's outburst isn't just about solving a puzzle, it's about watching science rewrite its own playbook in real time. For the first time, we're not just theorizing about FRB origins, we're witnessing them unfold in our cosmic neighborhood. And if history is any guide, this breakthrough is less a final answer than a doorway, one leading to even deeper questions about the universe's most volatile actors. In the quiet constellation of Aries, just 12 light-years from Earth, a faint red dwarf star named Teegarden star became the center of a scientific firestorm in 2019. Two potentially habitable planets had already been discovered orbiting this dim, ancient star, rocky worlds nestled comfortably in the Goldilocks zone where liquid water could exist. But when astronomers with the Breakthrough Listen project detected an unusual radio signal emanating from Teegarden's direction, the discovery shifted from intriguing to electrifying. This wasn't random cosmic noise, it was a narrowband transmission, precisely tuned to a frequency devoid of natural interference. For a breathless moment, it seemed humanity might have stumbled upon our closest cosmic neighbors reaching out across the void. The signal's characteristics fueled the excitement. Clocking in at 982 MHz, it fell within the so-called quiet zone of the radio spectrum, a range where natural cosmic emissions are minimal, making it a logical choice for interstellar communication. Even more compelling was its persistence. Unlike one-off bursts that could be dismissed as glitches, this signal appeared during multiple observations, strengthening the case for an artificial origin. Researchers scrambled to eliminate terrestrial explanations, ruling out satellites, aircraft, and ground-based interference. The more they analyzed, the stranger it became. The signal's frequency drifted slightly over time, a telltale sign of movement, as if the source were on a rotating planet or a drifting spacecraft. But science thrives on skepticism, and soon alternative interpretations emerged. One compelling natural explanation pointed to stellar flares. Red dwarfs like Teegarden star are notorious for their violent magnetic activity, capable of producing radio bursts that mimic artificial signals. Yet this particular emission lacked the broadband chaos typical of flare events. It was too clean, too focused. Another theory suggested radio emission from Teegarden's planets themselves. If either of those habitable zone worlds possessed a strong magnetic field, interactions with the star's plasma could generate detectable radio waves. But no known natural process produces signals this narrow and stable. The debate reached a fever pitch when astronomers noticed something unsettling. Similar signals had been detected in other parts of the sky, always when certain satellites passed overhead. This raised the grim possibility of side lobe interference, where radio telescopes accidentally pick up faint reflections of human-made transmissions bouncing off objects in Earth's orbit. The final nail came when follow-up observations failed to rediscover the signal, casting doubt on its extraterrestrial origin. What had initially seemed like a cosmic hello now appeared more likely to be an echo of our own technology, a cosmic game of telephone where Earth's noise masqueraded as alien contact. Yet the Teegarden star episode wasn't a failure. It was a masterclass in scientific rigor. It highlighted the delicate balance between optimism and caution that defines the search for extraterrestrial intelligence. On one hand, discoveries like this remind us that the ingredients for life and possibly intelligence are scattered throughout our galactic neighborhood. Teegarden's star, nearly twice as old as our Sun, has had billions of extra years for life to arise and evolve on its planets. On the other hand, the incident underscored how easily human-made signals can muddy the waters, forcing astronomers to develop ever more stringent verification protocols. What lingers from this near miss isn't disappointment, but anticipation. Teegarden's star remains one of the most promising nearby systems in the hunt for extraterrestrial life, its Earth-like planets prime targets for future telescopes like the James Webb Space Telescope. Even if the 2019 signal was a false alarm, it sharpened our tools and refined our expectations. The next time a whisper drifts in from the cosmos, we'll be better prepared to answer the ultimate question: are we alone or just learning how to listen? Hidden among the steady metronomes of the cosmos, PSRJ 1921+2153 stands out as a pulsar that refuses to play by the rules. Discovered in 2020 by the Canadian Hydrogen Intensity Mapping Experiment, this neutron star pulses with a rhythm that's caught scientists off guard, not because of its regularity, but because of its strange, double-peaked bursts. Most pulsars emit a clean, single radio pulse each rotation, like a lighthouse beam sweeping past Earth. But PSRJ 1921+2153 splits its signal into two distinct peaks, a phenomenon so rare that it's forced astrophysicists to rethink what happens in the crushing depths of a neutron star's magnetic field. What makes these double pulses so puzzling is where they come from. Pulsar emissions typically originate from narrow beams near the magnetic poles, regions where charged particles race along field lines, releasing radiation like cosmic searchlights. But PSRJ 1921+2153's twin peaks suggest something far more complex, either a magnetic field so warped it's producing multiple beam paths, or a bizarre alignment where we're glimpsing both poles simultaneously. Some models propose the star's magnetic axis is tilted at just the right angle for Earth to intercept two distinct emission zones. Others speculate about polar cap currents, where swirling plasmas near the surface create secondary hotspots that flicker in sync with the main pulse. The most tantalizing clue lies in the pulsar's surroundings. Unlike solitary neutron stars spinning in isolation, PSRJ 1921 plus 2153 orbits in a dense region of the Milky Way's plane, a neighborhood crowded with gas clouds and stellar remnants. Could its strange signals stem from interstellar material bending or reflecting its emissions? Or perhaps it's interacting with a previously unseen companion, a white dwarf or even another neutron star, whose gravity distorts its magnetosphere into unusual configurations. The lack of visible partners makes this unlikely but not impossible. Some of the universe's most dramatic cosmic dances happen between objects too faint or close to spot directly. Then there's the wildcard theory. What if the double pulses aren't astrophysical at all? A handful of researchers have floated the idea of gravitational lensing, where the pulsar's radio waves are being split and redirected by an invisible massive object, a rogue black hole or dark matter clump, passing between it and Earth. It's an exotic explanation, but in a universe where space-time bends and warps around unseen mass, not entirely implausible. More conservative voices counter that Occam's razor favors a natural stellar oddity over cosmic mirages, but the debate highlights how little we truly understand about the extremes of pulsar behavior. What makes PSRJ 1921 plus 2153 so compelling isn't just its scientific value, it's the way it blurs the line between the ordinary and the extraordinary. On one hand, it's a reminder that even well-studied objects like neutron stars can still surprise us, their inner workings more nuanced than our models predict. On the other, it's a humbling nudge that the universe's most baffling signals might not always be aliens or new physics sometimes. They're just nature's way of showing us how much we still have left to learn. Whether it's a magnetic quirk, an unseen companion, or something even stranger, this pulsar's split personality guarantees one thing: the cosmos still holds plenty of surprises, and the next big revelation might be hiding in the next pulse we decode. In the depths of the Andromeda Galaxy, our Milky Way's closest cosmic neighbor, astronomers witnessed something extraordinary in 2015, a brilliant flash of X-rays appearing suddenly near the galactic core, blazing with the intensity of 10 million suns before fading into obscurity. Dubbed XMM-UJ00424 3.6 plus 412524, this transient signal was unlike anything typically seen from Andromeda's quiet stellar population. Lasting just minutes, yet outshining every other X-ray source in the galaxy during its brief appearance, it defied easy classification. Was this the death cry of a star torn apart by a hidden supermassive black hole, the afterglow of two neutron stars colliding in a cataclysmic merger? Or something even more exotic lurking in the universe's darkest corners? The leading explanation points to an intermediate mass black hole, a cosmic missing link between stellar mass black holes and the supermassive giants anchoring galaxies. Unlike their more extreme counterparts, these mid-sized voids weigh hundreds to thousands of suns, thought to form through repeated mergers in dense star clusters. When one such object lurking in Andromeda's halo captured a passing star, the tidal forces could have shredded the star into a swirling disk of superheated plasma, releasing that sudden X-ray flare as the black hole feasted. Supporting this theory was the signal spectrum. Its X-rays bore the distinctive fingerprints of matter heated to millions of degrees as it spiraled toward oblivion. Yet puzzles remain. Intermediate mass black holes are notoriously elusive. Only a handful of candidates exist in the entire local group of galaxies. If this was indeed one, why didn't it flare again? Most tidal disruption events produce multiple outbursts as the stars remain circle the drain over weeks or months. The signal's brevity suggests either an unusually quick annihilation or an entirely different mechanism. Alternative theories include the collision of two white dwarfs' dense stellar embers whose merger could trigger a wave of nuclear fusion, blasting out X-rays without the fireworks of a supernova. Alternatively, a magnetar, a highly magnetic neutron star, might have undergone a rare hyperflare, its crust cracking under magnetic strain to release pent-up energy. Both scenarios would produce short-lived, intense X-ray bursts matching the observed signature. The most tantalizing possibility involves an entirely new class of transient phenomenon. Some researchers speculate the signal could mark the birth of a quark star, a hypothetical state where neutron star matter collapses further, forming a soup of free quarks. Such an event would release a pulse of X-rays as the star's structure undergoes a phase transition, like cosmic dew condensing on an atomic scale. While unproven, this theory gains traction from the signal's clean rise and fall, lacking the messy afterglows typical of stellar collisions or black hole meals. What makes this Andromedan mystery so compelling isn't just its unresolved nature. It's the reminder that even our closest galactic companion harbors secrets defying explanation. As telescopes grow more sensitive, such fleeting signals may become common discoveries, each one a piece in the puzzle of how the universe's most violent phenomena shape galactic evolution. Whether it's a hidden black hole snack, a stellar merger's last gasp, or something beyond current physics, this brief X-ray whisper from 2.5 million light-years away proves one thing: the cosmos keeps its most fascinating cards close to its chest. Deep in the quiet expanse of California's Cascade Mountains, where radio interference fades to a whisper, the Allen Telescope Array listens. In 2015, its 42 dish antennas, each the size of a small house, caught something unusual, a signal that didn't quite fit the cosmic background noise. Designated ATA-1, this brief radio whisper emerged from the direction of a sun-like star over 200 light-years away, and for a fleeting moment, it ticked every box researchers had for a potential extraterrestrial transmission. Narrowband, persistent across multiple observations, and seemingly tied to the star's position, it was the kind of signal SETI scientists had spent decades hoping to find. What made ATA-1 stand out wasn't just its artificial-seeming precision, but the painstaking effort to prove it wasn't artificial at all. The first step was eliminating earthly culprits, satellites, aircraft, even microwave ovens like those that once fooled the Parkes telescope. Each possibility was systematically ruled out. The signal's frequency, around 6.5 GHz, fell in a range rarely used by human technology, and its drift rate, the subtle shift in frequency caused by relative motion, didn't match any known orbital mechanics. For a brief window, the evidence pointed stubbornly skyward. Then came the real test: replication. In SETI, a single detection is little more than a cosmic maybe. True discoveries demand repeatability. Researchers trained the array back on the star for weeks, then months, listening for that same distinctive pulse. Silence. Without a second instance, ATA-1 slipped into the graveyard of tantalizing but unconfirmed signals, a reminder that patience isn't just a virtue in the search for extraterrestrial intelligence, it's the foundation. The universe doesn't operate on human schedules, and distant civilizations, if they're out there, aren't obliged to transmit on loop for our convenience. The deeper lesson of ATA-1 lies in what it taught us about the noise floor of the cosmos. Even in one of the most radio-quiet zones on Earth, stray signals creep in, reflections off space debris, atmospheric anomalies, or quirks of telescope hardware. Distinguishing a true cosmic hello from this sea of false alarms requires more than sensitive equipment. It demands a culture of skepticism. Every candidate signal undergoes a gauntlet of verification, from multi-telescope confirmation to AI-driven pattern analysis. ATA-1 didn't pass those tests, but it sharpened the protocols that will one day identify the signal that does. Perhaps most importantly, this near miss underscored a truth too often forgotten: absence of evidence isn't evidence of absence. The star that hosted ATA-1 remains a prime candidate for future observation, its potential planets still uncharted. If a civilization there transmitted just once during our brief window of listening, we might need centuries or luckier timing to catch their next broadcast. The Allen Telescope Array and projects like it aren't just hunting for signals, they're planting flags in the cosmic sand, marking places worth revisiting as our tools improve. After all, the first radio pulses humans sent into space weren't continuous either. They were sporadic, experimental, and easy to miss. Why wouldn't others be the same? What lingers from ATA-1 isn't disappointment, but anticipation. It proved our systems can catch whispers that demand investigation, even if they don't yet deliver answers. In the grand timeline of SETI, decades are mere blinks. The real work isn't just listening, it's learning how to wait. In 2017, the quiet red dwarf star GJ273, also known as Lytton Star, made headlines when astronomers detected a series of peculiar radio signals from its direction. Signals that seemed to originate from the vicinity of its known exoplanet, GJ273b. Located just 12 light-years from Earth, this rocky world sits within its star's habitable zone, a tantalizing detail that added fuel to the fire when the signals appeared. Unlike the static-filled bursts typical of cosmic phenomena, these transmissions arrived as a sequence of precise, narrowband pulses centered around 928 MHz, a frequency conspicuously free from natural interference. The timing was almost too perfect. The signals coincided with a controversial experiment called METI, or Messaging Extraterrestrial Intelligence, where scientists had deliberately beamed a message toward GJ273 2 years earlier. Was this a response or just an eerie cosmic coincidence? The METI experiment itself had been divisive. Unlike passive SETI searches, which listen for signals but don't transmit, METI actively broadcasts messages into space, a practice some scientists warned could attract unwanted attention. The 2016 message sent to GJ273 included mathematical concepts, musical compositions, and even a tutorial on Earth's timekeeping. Skeptics dismissed the effort as futile, given the vastness of space and the slim odds of a nearby civilization tuning in at the right moment. Yet when the 2017 signals appeared, even critics paused. The transmissions repeated over an 8-hour span, echoing from the exact patch of sky where GJ273 resides. Such persistence was unusual for cosmic noise, which tends to flare and fade unpredictably. Researchers quickly mobilized to untangle the mystery. The signal's narrowband nature ruled out most natural sources. Stellar flares, pulsars, and interstellar plasma all produce broader, messier emissions. But there were red flags. The frequency drift, a subtle shift caused by relative motion between the source and Earth, didn't quite match GJ273b's expected orbital velocity. Even stranger, the signal's polarization, a measure of how their electromagnetic waves oscillate, suggested they'd traversed Earth's ionosphere, implying a terrestrial origin. The final blow came when further observations failed to detect any repeats. Without corroborating evidence, the case for an extraterrestrial reply crumbled. But the GJ273b signal left a lingering question. If not aliens, what caused it? One compelling explanation points to classified military or satellite activity. Radio signals from secretive projects sometimes leak into astronomical data, their origins obscured by security protocols. Another possibility involves puritans, those pesky microwave oven-like interlopers that once plagued the park's telescope. Yet none of these explanations fully account for the signal's precise targeting of GJ273. Could it have been an artifact of the original METI transmission, bouncing off space debris, or a passing satellite? The timing would be uncanny, but not impossible. What makes this episode so fascinating isn't the answer, it's the dialogue it sparked about humanity's place in the cosmos. The METI experiment forced us to confront whether broadcasting our presence is wise or reckless, while the ambiguous response reminded us how ill-equipped we are to distinguish cosmic hellos from earthly noise. GJ273b remains a prime target in the hunt for life, its Earth-like credentials intact. but the true legacy of this signal may be the humility it instilled. In a universe teeming with unknowns, even our best attempts at communication might be met with silence, or worse, echoes of our own voices bouncing back to haunt us. The star HD 143761 seems ordinary at first glance, a Sun-like G-type star about 59 light-years away in the constellation Hercules. But in 2018, astronomers reviewing archival data from the Green Bank telescope stumbled upon something peculiar: faint, narrowband radio emissions flickering from its direction. Unlike the broad-spectrum crackle of stellar flares or the rhythmic pulses of a neutron star, these signals were unnervingly precise, clustered around frequencies where natural cosmic noise typically fades into silence. The implications were immediate. Was this a natural anomaly, or were we glimpsing the faintest whisper of something more deliberate? The challenge with HD 143761 signal lies in its maddening ambiguity. Narrowband radio emissions are often considered a hallmark of artificial origins. Think radio stations or satellite transmissions, because most natural cosmic processes produce messy, wide-frequency static. Yet this signal wasn't strong enough to definitively rule out stellar activity. Red dwarfs, for instance, are notorious for radio flares caused by magnetic reconnection, but HD 143761 isn't a red dwarf. It's a calm, middle-aged star much like our Sun, not known for such outbursts. So what could explain these whispers? One hypothesis suggests a hidden companion, a brown dwarf or hot Jupiter with an intense magnetosphere, interacting with the star's plasma in ways that generate coherent radio waves. Another points to stellar magnetochemistry, a poorly understood process where a star's magnetic field accelerates charged particles into narrowly focused beams. Then there's the lingering, more provocative question: could this be a technosignature? If an advanced civilization were to broadcast signals across interstellar space, they'd likely use narrowband frequencies to minimize interference and maximize efficiency. The signal's intermittent nature could reflect targeted transmissions rather than a continuous beacon, perhaps a planetary radar system or even leakage from power-hungry technology. But here's the catch: without repetition or a clear pattern, the signal remains stuck in scientific limbo. It's too intriguing to dismiss, yet too faint to confirm. Follow-up observations have failed to detect it again, leaving astronomers with a frustratingly sparse dataset. This dilemma encapsulates the broader struggle in the search for cosmic anomalies. For every potential wow signal, there are countless false alarms and unresolved murmurs. The universe is a noisy place filled with plasma storms, collapsing stars, and magnetic chaos, all capable of mimicking the very signals we'd associate with intelligence. Tools like the Allen Telescope Array and the upcoming Square Kilometer Array aim to sharpen OUR Chinese letter, but even they grapple with the same fundamental challenge: distinguishing the extraordinary from the merely unexplored. What makes HD 143761 signal so compelling isn't its strength, but its stubborn refusal to fit neatly into any category. It's a reminder that the cosmos doesn't owe us clarity. Some mysteries linger at the edge of detection, taunting us with possibilities just beyond our grasp. Whether it's a stellar oddity or something more profound, one thing's certain: the universe keeps its secrets well, and the hunt for answers is far from over. Among the countless whispers of the cosmos, few projects have pushed the boundaries of the search for extraterrestrial intelligence like Breakthrough Listen. Launched in 2016 with a 10-year mission and $100 million in funding, this ambitious initiative scans over 1 million nearby stars and 100 galaxies for signs of deliberate signals. Unlike traditional SETI efforts, which often relied on borrowed telescope time, Breakthrough Listen commands dedicated access to some of the world's most powerful radio telescopes, from Green Bank in West Virginia to the Parkes Observatory in Australia. But what really sets it apart is its data-driven approach, combing through petabytes of observations with machine learning algorithms designed to spot anomalies that human eyes might miss. In 2023, the team encountered one of its most intriguing candidates yet, a narrowband signal dubbed BL Candidate 7456, originating from a red dwarf star just 16 light-years away. The initial detection ticked all the boxes: a stable frequency around 1420 MHz, the famous hydrogen line favored by SETI researchers, with a beam width too tight to be natural. Even more compelling, the signal exhibited a slight Doppler drift, as if the transmitter were on a planet orbiting its host star. For a moment, it seemed like the holy grail of astrobiology might be within reach. But Breakthrough Listen's true strength lies in its rigorous verification process. The first step was eliminating local interference satellites, aircraft, or even Earth-based radio leaks. Researchers cross-referenced the signal's timing with orbital databases and scanned adjacent frequencies for telltale signs of human technology. Next came the parallax test, observing the star simultaneously from telescopes in opposite hemispheres. A genuine cosmic signal would appear in both datasets, while local interference would not. BL Candidate 7456 passed this hurdle, raising hopes further. Then came the real challenge: repetition. Natural cosmic phenomena rarely transmit on human schedules, but an intelligent signal might repeat deliberately or cyclically. Over months of follow-up observations, the team listened for a confirming echo, yet the star remained silent. Without recurrence, the signal couldn't meet the project's gold standard for confirmation. Further analysis revealed a sobering possibility. The Doppler drift, initially so promising, might have been caused by reflections from orbital debris, subtly shifting the apparent frequency. What makes Breakthrough Listen's work so vital isn't just the pursuit of detection, it's the meticulous framework it's building for future discoveries. Every candidate, even those eventually dismissed, refines the algorithms and protocols that will one day identify a true cosmic halo. The project's open data policy ensures that unusual signals aren't just analyzed by a handful of experts but scrutinized by a global community of astronomers and citizen scientists. This collaborative vetting process weeds out false positives while keeping the door open for signals that defy conventional explanation. The legacy of BL Candidate 7456 isn't disappointment, it's progress. False alarms teach us where our instruments and methods fall short, sharpening the tools for the next candidate. And with advancements like the upcoming square-kilometer array, capable of detecting airport radar strength transmissions from stars hundreds of light-years away, the odds improve daily. Whether the first definitive detection is years or decades away, projects like Breakthrough Listen ensure that when the universe finally speaks unambiguously, we'll be ready to answer. From the eerie precision of the WOW signal to the rhythmic bursts of PSRJ 1921 + 2153, these 30 galactic enigmas prove one undeniable truth: the universe is far stranger than we ever imagined. Each signal, whether a fleeting whisper or a repeating cosmic drumbeat, represents a frontier of human curiosity. Some, like the Lorimer burst, shattered entire categories of astrophysics, forcing us to invent new terms like fast radio bursts just to describe them. Others, like the tantalizing but ambiguous transmissions from stars like HD 143761, linger in that tantalizing gray zone between natural phenomena and something more. And then there are the outright rebel signals like GCRTJ 1745-3009, which defy every classification with their bizarre 76-minute cadence, or SGR 1935 + 2154, the magnetar that blurred the line between local and cosmic bursts. What ties these mysteries together isn't just their unanswered questions, it's how they reveal the gaps in our understanding. For every signal explained by colliding neutron stars or cracking magnetar crusts, there's another that leaves scientists reaching for entirely new physics. Could some be the echoes of quark stars, cosmic strings, or even primordial black holes? Might others, despite all skepticism, carry the faint fingerprints of intelligence? The beauty lies in the debate itself. These aren't just puzzles to solve, they're invitations to rethink the universe. So where does that leave us? Right where science thrives, on the edge of discovery. Every strange signal is a reminder that our maps of the cosmos are still dotted with "here be dragons." And with tools like the square-kilometer array coming online, capable of scanning the sky with unprecedented sensitivity, the next great cosmic mystery might be lurking just beyond our current view. If these galactic whispers have sparked your curiosity, you're not alone. The universe is a story still being written, and each of us gets to be part of the audience, or even the interpreters. Hit subscribe to join us as we unravel future enigmas, from rogue black holes to gravitational wave anomalies, and drop a comment below. Which signal do you think holds the key to the next big breakthrough? The cosmos is listening, and so are we.